In this section, I'm going to be introducing a number of properties of functions, as well as revisiting some properties that were discussed earlier, such as symmetry and periodicity. When solving problems involving functions, often it's helpful to know if the functions possess any type of symmetry, for example, even or odd symmetry. The reason for this is if functions are symmetric, there's a high degree of redundancy in their graphs. In other words, half of the graph of the function is redundant because it can be determined by the other half of the graph of the function. And we can often exploit this symmetry in order to make it easier to solve problems. Sometimes, for example, reducing the amount of work we need to do by a factor of 2, because maybe we can prove that some result is true for half of the graph of the function, maybe for the positive part of the horizontal axis, and then say by symmetry it's true for the other half. So we can sometimes, for example, reduce the amount of work we need to do. So for this reason, if we're performing mathematical operations, basic arithmetic operations such as addition and multiplication on functions that have symmetry, we might be interested in whether or not the resulting function, in other words, the sum or product of these functions, also has some kind of symmetry. And this is what's being discussed on this slide. So if we start with addition, or summing functions, if we sum two functions that have even symmetry, the result is even. If we compute the sum of two odd functions, the result is odd. And if we sum an even function and an odd function, the result is neither even nor odd, assuming that neither of the functions being added is identically 0. And I guess you could kind of argue that if one of the functions you're adding is 0, you're not really adding anything because adding 0 doesn't change the result. And the basic pattern that we have in the above cases that I just mentioned is essentially when you're adding functions, the sum of functions that have the same type of symmetry produces a result with the same type of symmetry. In the case of multiplication, the product of two even functions is even, the product of two odd functions is even, and the product of an even function and an odd function is odd. So the pattern that we have here is when we're computing products, the product of functions that have the same type of symmetry will result in an even function, and the product of functions with opposite types of symmetry, for example, one of them is even, one of them is odd, will produce an odd result. Sometimes we may be solving a problem involving functions, and it would be very convenient if the functions involved had symmetry. In other words, they were either even or odd. But because of the nature of the problem, we can't guarantee that they have any type of symmetry because they're just arbitrary functions which don't necessarily have to have symmetry. In this regard, there's a result which is stated on this slide which is very useful, which effectively can allow us to turn any problem involving any arbitrary function into one which involves only symmetric functions. So let's look at what this result says. So every function x has a unique representation of the form given by this equation here, where the function xe is an even function and the function xo is an odd function. So what this particular result is saying is that any function, regardless of whether it's even or odd, in other words, it doesn't have to have any symmetry at all, can always be written as the sum of an even function and an odd function. And furthermore, this representation is unique. In other words, for any given function x, there's only one choice that you can make for xe that's even, and one choice that you can make for xo that's odd, such that this equation is satisfied. And in particular, the choice you need to make for xe and xo are these. So xe has to be chosen in this way. So xe is essentially the sum of the original function x plus its time-reversed version, and then we're dividing by 2. So effectively it's the average of the original function x and its time-reversed version. And then xo is given by this formula here, which is almost the same as the formula for xe. The only difference is a plus sign has been changed to a minus sign. And as a matter of terminology, the function xe and the function xo are referred to as the even part and the odd part of x respectively. And for convenience, as a matter of notation, the even and odd parts of x are denoted by even x and odd x respectively. Now at this point I'd like to consider an example, and in particular the example I'd like to consider is essentially doing a partial proof of the result that's stated at the top of this slide. In this example, what we have is the result from the earlier slide stated in the form of a theorem, that any arbitrary function x can be uniquely represented as a sum of an even function xe and an odd function xo, where xe and xo are given by these equations here. And what we want to do in this example is actually prove that this theorem is correct. We're only going to do a partial proof. We're going to skip the fact that the decomposition is unique. We won't prove the uniqueness, but we're going to show the rest of the theorem is correct. So to begin with, we're going to show that xe plus xo equals x. So to do this, we just take the formulas for xe and xo. So xe is given by this equation here, and xo is given by this equation here. We're going to simply add them together. So the first circled quantity is the formula for xe. The second circled quantity here is the formula for xo, and then we're going to simply add them. And what happens when we add them and simplify, a bunch of terms are going to cancel, and all we'll be left with is x of t. So in fact, xe plus xo does equal x. So this proves that essentially this equation here is correct. When we add these functions together, xe and xo, in fact we do get x back. The next thing I want to do is I want to confirm that xe is in fact an even function and xo is in fact an odd function. So let's start with showing that xe is an even function. So the way that we're going to do this is we're going to take the formula from xe from above, which is this formula here, and we're going to substitute minus t for t. In other words, we're going to evaluate this function at minus t. So if we do this, we're going to get this right-hand side here just by substitution. And then we can simplify and rearrange this to get the equation on the right hand, or the formula on the right hand side, into this form here. And now we can simply observe that this expression here is simply the expression for xe up above. It's the same as this expression. So therefore this quantity here on the right hand side is equal to xe. And now we've shown that xe is even, because what we have overall is xe of minus t is equal to xe of t. And since this is true for all t, by definition the function xe is even. And the steps that we've gone through here is how you would show that a function is even in general. So this is a helpful thing to know, because sometimes we may have to show that a function is even in other problems that we're solving. To show that xo is odd, the way we go about this is we start out with our formula for xo, and then we're going to substitute minus t for t in this formula. So this gives us this first line here. And then all we're going to do is simplify the right-hand side and rearrange it a little bit to get to this next line, just using straightforward algebra. And now we can observe that this quantity here on the right-hand side is the negative of xo of t. In other words, it's the negative of this quantity here. So we can replace it by minus xo. And now overall what we have here is that xo of minus t is equal to minus xo of t. And since this is true for all t, this means that the function xo is odd. And again, the steps that we went through here are helpful, because this is how we would show in general how a function is odd, like how we would show a function is odd. And this can be useful for a lot of other types of questions that are not proof type questions. And this is part of the reason why I wanted to go through this example. Often when we're working with periodic functions, we find ourselves adding periodic functions together. And sometimes we may wonder whether that sum, in other words the sum of two periodic functions, is itself periodic, and if so, what's the fundamental period? Now, it turns out that when you add periodic functions together, the result that you get is not necessarily a periodic function. In other words, it could be aperiodic. So this is not a completely trivial thing to determine. In other words, to figure out whether or not the sum of two periodic functions is periodic is not completely trivial. And essentially what we have on this slide is a theorem that allows us to make the determination of whether the sum of two periodic functions is in fact periodic, and if it is, what the fundamental period is. So let's take a look at this theorem in more detail. So essentially what it says is if we have two periodic functions which are denoted by x1 and x2, and these functions have the fundamental periods capital T1 and capital T2 respectively. So T1 is the fundamental period of x1 and T2 is the fundamental period of x2. And let y denote the sum of the functions x1 and x2. So y is what we're trying to determine whether it's periodic or not. Then we can make the following statements. So the first part of the theorem is saying whether or not y is periodic. So y is periodic if and only if the ratio of the fundamental periods, T1 over T2, is a rational number. And you'll remember from earlier in the course, a rational number is simply a number that's the ratio of integers. Now, if the sum of the two functions x1 and x2 is periodic, in other words, if y is periodic, this theorem goes on to say what the fundamental period of y actually is. And in particular, the fundamental period of y is given by RT1, or equivalently, it can be computed as q times t2, where q and r are defined by this relationship here. In other words, q and r are simply the ratio of t1 over t2 expressed such that q and r are coprime. In other words, they have no common factors. So saying this another way, the fraction q over r is simply equal to the fraction t1 over t2, but it's written in most reduced form, so you've cancelled any common factors between the numerator and denominator when you write the fraction q over r, whereas t1 and t2 may have common factors between them. And just as a comment to the side, the quantity r times t1, or equivalently q times t2, because it turns out they'll always be equal, these are simply what's called the least common multiple of t1 and t2. Now, although the theorem that we just looked at only covers the case of adding two periodic functions together, we can use this theorem to test the sum of any number of periodic functions. So if I have n periodic functions that I'm adding together and I want to determine whether the sum is periodic, and if so, what the fundamental period is, I can just apply this theorem n minus 1 times. So by repeatedly applying this theorem, I can handle any arbitrary number of periodic functions that are being added together. At this point, I'd like to do a couple of examples to help illustrate the use of the theorem introduced at the top of this slide. And I'd like to begin with example 3.2. In this example, we're given two periodic functions, x1 and x2. And we're asked to determine whether the sum of these functions, which we're calling y, is periodic. And in order to do this, we're going to use the theorem that was introduced just a short time ago. So the first thing we need to do is we need to find the fundamental periods of x1 and x2. So the first observation we can make is both the function x1 and the function x2 are sinusoidal functions. In other words, they're functions of the form sine alpha t for some real alpha. So we can find the fundamental period of these functions just using this formula here. It's 2 pi over the magnitude of alpha. In other words, the magnitude of whatever constant is multiplying the t. So if we look at the function x1 to compute its fundamental period, because we have this constant pi here, the fundamental period of x1 will simply be 2 pi divided by this constant pi. In other words, it will be equal to 2 when we simplify. And the fundamental period of the function x2, because there's a 1 in front of this t here that we don't bother to write, the fundamental period will be 2 pi divided by the 1 that's multiplying the t. In other words, we have 2 pi over 1, which simplifies to 2 pi. So the next thing we need to do is we need to take the ratio between t1 and t2. And if this ratio is a rational function, then the sum of x1 and x2, in other words, the function we're calling y, will be periodic. Otherwise, it won't be periodic. So if we plug in the values for t1 and t2 that we calculated up above and simplify, the ratio of t1 to t2 simplifies to 1 over pi. And because pi is an irrational number, 1 over pi also is an irrational number. In other words, it's not rational. Since this ratio of t1 over t2 is not a rational number, the conclusion that we draw is the function y, in other words, the sum of x1 and x2, is not a periodic function. The next example that I'd like to consider is example 3.4. In this example, we're given two periodic functions, x1 and x2, and we're asked to determine whether the sum of these functions, which we're calling y, is periodic. And if it is periodic, we're asked to find the fundamental period. So again, we're going to use the theorem that was introduced a little bit earlier in order to do this. So first of all, we need to compute the fundamental periods of x1 and x2. So I'm going to call the fundamental period of x1 t1, and I'll call the fundamental period of x2 t2. So to compute the fundamental period of x1, if we look at x1, x1 is just a real sinusoidal function, and the fundamental period of such a function is just going to be 2 pi divided by the absolute value of the constant that multiplies the t here. So we'll just have 2 pi over 6 pi, which simplifies to 1/3. And then for computing the fundamental period of the second function also is a real sinusoidal function. So the fundamental period is going to be 2 pi divided by the absolute value of this constant 30 pi. So 2 pi over 30 pi, which simplifies to 1/15. So now we have both of the fundamental periods. To figure out whether the function y, in other words the sum of x1 and x2, is periodic, we need to take the ratio of t1 to t2 and check to see if this ratio is a ratio of integers. So if we substitute in the values that we computed for t1 and t2, we have 1/3 and 1/15, and we compute the ratio between them, we get 15 over 3. And if we cancel any common factors between the numerator and denominator, we get 5 over 1. Well, clearly 5 over 1 is a ratio of integers. This is a rational number. Therefore, the conclusion that we draw is the sum of x1 and x2, in other words the function we're calling y, is in fact periodic. And now we need to find the fundamental period. So to find the fundamental period, we can either take t1 times the denominator here, which is 1, or take t2 times this numerator 5 here. It makes no difference. They'll both give us the same answer. In other words, we have kind of a cross multiplication pattern, if this helps you to remember how to do this computation, where basically we have our ratio t1 over t2, and then we have the ratio written in most reduced form, so any common factors are cancelled between the numerator and denominator. In other words, p and q are coprime. That is, they have no common factors. And in this case, 5 over 1 is 5 and 1 are coprime. We've cancelled any common factors. So we can simply take t1 times 1 or 5 times t2. Both of them will always be equal, and this will be the period of the function y. So because I prefer to multiply by 1, because I can usually do this even on a bad day, the period 1 times t1 gives us our period for the function y. So if we plug in the value of t1 that we computed, we plug in a value of 1/3. 1 times 1/3 is 1/3, so therefore the fundamental period of the function y is 1/3. Equivalently, we could have computed 5 times t2, in which case we still would have got an answer of 1/3. Often when working with functions, we're interested in the places where functions are non-zero. So on this slide and the next few slides, I need to introduce some terminology that relates to this notion of when is a function zero versus when is it non-zero. So the first term I need to introduce is right-sided. So a function x is said to be right-sided if for some finite real constant t0, a condition of this form is satisfied. And basically what this is saying in terms of a graph of the function is that there exists some point on the graph of the function which we'll call t0, such that everywhere to the left of this point the function is equal to 0. So the word right in the term right-sided is actually referring to the places where the function is potentially non-zero. So it's a little bit confusing in the sense that the definition actually is saying something about where the function is 0, but the word right in the definition is referring to the place where it's not potentially non-zero. An example of a right-sided function would be the function that's shown in this graph here. This function x is right-sided because there exists a place on the horizontal axis, which I'm going to call t0 here, such that everywhere to the left of it the function is 0. In other words, the function is only potentially non-zero to the right of t0. Another term I need to introduce is the term causal. So a function x is said to be causal if it satisfies a relationship of this form. And all this is just a special case of a right-sided signal where the value t0 from up above is specifically the value 0. So essentially what this is saying is the graph of the function is 0 everywhere on the negative part of the horizontal axis. Now, I just want to briefly comment on terminology. Sometimes we overload terms in signals and systems. In other words, you use the same word to mean completely different things in different contexts. And causal is one such word. In this particular context here, we're using the word causal to describe a function. So that we're talking about a causal function. Later on, we'll be using the word causal to describe a system. These are two completely different things. And in some sense, this use of the word causal on this slide makes a lot less sense because the word causal in plain everyday English deals with cause and effect. But there's not anything involving cause and effect here. The notion of a causal function is a very simple definition which simply relates to where the function is non-zero and where it's 0. On this slide, I need to introduce yet more terminology that relates to this notion of when is a function zero or non-zero. So the first term I need to introduce is the term left-sided. So a function x is said to be left-sided if for some finite real constant t0, a condition of the following form is satisfied. So in terms of the graph of the function, what this particular condition is saying is that there exists some point on the horizontal axis which we'll call t0, such that everywhere to the right of this point the graph of the function is zero. In other words, the word left and left-sided is identifying the place where the function is potentially non-zero. So it's equal to 0 to the right of the point t0, and it's potentially non-zero to the left of that point. So an example of a left-sided function is shown in the graph in the middle of the slide, this function here that's labeled as x. This function is left-sided because there exists a point which I'll call t0, such that everywhere to the right of this point the graph of the function is 0. Another term I need to introduce is the term anti-causal. So a function x is said to be anti-causal if it satisfies a relationship of this form. And all this is just the condition that we have up above here, where t0 is chosen specifically to have the value 0. So an anti-causal function is just a special case of a left-sided function. And I just want to point out in terms of terminology, in this course we overload the term anti-causal. We use anti-causal as we've done here to describe a function, but later on in the course we'll use the word anti-causal to describe a system. And these two uses of the word anti-causal in some sense have nothing to do with one another. They have very different meanings. The meaning here is a very simple one. An anti-causal function is simply a function that's 0 for some particular range of the independent variable t. Whereas an anti-causal system is something more complicated, which involves cause and effect. And lastly, on this slide, I have just a few more definitions that relate to this notion about when is a function 0 versus non-zero. So I need to introduce the terms finite duration and two-sided. So a signal is finite duration if it's both left-sided and right-sided. Sometimes we also use the word time-limited. It means the same thing as finite duration. So an example of a finite duration function is what's shown in this figure here at the top of the slide. This function is a finite duration function because there exists some point such that everywhere to the left of it the function is 0, in particular this point t0, and there also exists a point t1 such that everywhere to the right of it the function is 0. So the function is both left-sided and right-sided. The last term I need to introduce is the term two-sided. So a function that's neither left-sided nor right-sided is called two-sided. An example of a two-sided function is what's shown in the bottom of the slide here. And by the dot 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 here, I'm trying to convey by these dot dot dots on the left and right hand side of the graph is the function doesn't ever go to 0 and stay at 0 as you go to negative infinity or positive infinity. This would be an example of a two-sided function, because presuming that the function never goes down to 0 out here and stay at 0, and it never goes down to 0 out here and stays at 0, there's no point that I can choose along the axis such that everywhere to the left of it or everywhere to the right of it the function is 0. Therefore this function is neither left-sided nor right-sided. Next I need to introduce the notion of a bounded function. So a function x is said to be bounded if there exists some finite positive real constant a such that a condition of the following form is satisfied. And essentially what this condition is saying is the function is never infinite. For any value of t, the function is never infinite. It's always finite. Because if there was even a single point where the function x was infinite, there would be no choice that you could make for a that's finite that would satisfy this inequality. Some examples of functions that are bounded would be sinusoidal functions like sine and cos. The sine function is bounded because its magnitude is always less than or equal to 1. And a cosine function also is an example of a bounded function because for all values of t, the magnitude of cos t is less than or equal to 1, which is a finite constant. In contrast, functions like the tangent function or any non-constant polynomial function are unbounded. The tangent function is unbounded because if you evaluate it, for example, at pi by 2, it blows up to infinity. And similarly, any polynomial function, for example denoted by the function p here, that's a non-constant polynomial function, for example something like a quadratic like t squared, it's unbounded, because if you evaluate such a function at either plus infinity or minus infinity, the function value will blow up to infinity. So a function like this would also be unbounded. Now I need to introduce the concept of energy and power for functions. So the energy E that's contained in a function x is given by an equation of this form. So essentially the energy of a function is simply the magnitude of the function squared, and then we integrate that over the whole domain of the function, in other words over the entire real line. And just as a matter of terminology, a function with a finite amount of energy is called an energy signal. We can also define average power, which is denoted by P on this slide. Average power is simply energy per unit time. So if you look at the way it's defined, so the average power in the signal x is given by this equation, what we're doing is we're taking the magnitude squared and integrating it. So this is essentially measuring energy. And we're taking this integral over larger and larger intervals, because t is going to infinity in this limit. So these limits are getting larger and larger, approaching infinity, and then we're dividing by the length of the interval. So this is going to give us energy per unit time, which is essentially what average power is defined as. So just as a matter of terminology, a signal with non-zero finite average power is said to be a power signal.